Hi, I'm Tyler Coles, lead software engineer on the Epymorph project at Northern Arizona University. Epymorph is a Python software library that aims to provide a simplified framework for completing the full life cycle of a spatial epidemiological modeling experiment. It is now available in a version 1 beta release, and you can install it from PyPI, view our Git repository, and find more information on our documentation site. This video will introduce the library and provide a taste of its features in a hypothetical scenario. We will assemble and run a forward simulation of the spread of a fictional disease using built-in modular components and automatically fetch required input data for our model. But before we get to the scenario, I'll describe what we think makes Epymorph such a powerful tool for epidemiological modeling. There are several common approaches to modeling disease spread, and Epymorph fits in the category of spatially explicit, stochastic, compartmental models of discrete populations. These models are capable of exploring how the spread of an infectious pathogen is influenced by movement patterns of host populations. Whereas previous epi models commonly combine disease mechanics and movement mechanics into one system of equations, Epymorph decouples these. By making our disease model independent from our movement model, each becomes simpler to develop and reason about, easier to share with others, and possible to swap for alternative models, leading to rapid combinatorial exploration. We will call our disease model an intrapopulation model, or IPM, and we call our movement model, appropriately enough, or MM for short. This modular design philosophy is applied throughout the library, and we'll see how Epymorph's modularity really accelerates our ability to experiment with epi models. Okay, now let's get to our scenario. Now, for the purposes of our little experiment today, let's assume we are a set of epidemiologists and public health experts representing state and county interests. So maybe we will want to model at the county granularity so we can get some good model data that might be useful on a county scale. And we'll focus in the four corner states of Arizona, Colorado, New Mexico, and Utah. So here we have that map of those four states here with their counties outlined. And in the scenario, we want to model some hypothetical outcomes for infectious disease spread. And we're going to start with a simple SIRS model. This is a fairly canonical compartmental model in the epidemiological space. We'll want to model movement as well, and we will use a, again, fairly simple distance kernel movement that sort of mimics human commuting patterns. And we will focus on the first 5 months of 2020, just for a time frame, and we'll assume that our population is naive to this pathogen and that we can treat them uniformly. In other words, there's one risk strata that we're worried about. Okay, so we will model that scenario, and here I am in a Jupyter notebook, which is an excellent place to experiment with Epymorph in an interactive way. I already have a virtual environment set up, and I've installed Epymorph in that virtual environment. And I've divided this talk up into 3 parts. First, we will set up and run a forward simulation, that is, starting from a set of initial conditions. We will run our simulation forward in time for a set period of time, and we'll do that just once and then look at the output. In the second part, we will use tools to process and visualize the output. And in part 3, we'll get to really kick the tires of Epymorph's modular design and see how that all works. Now, the first step to using Epymorph in a program is, of course, to import the required components. Because that can be kind of a pain in some libraries, we wanted to provide a starter kit of imports that gives you most of the commonly used elements of a simulation. So we can do from epymorph.kit import star, and that's going to give us most of the things that we need. Now we'll start by constructing what we call a room, or runnable modeling experiment. And this is going to define our simulation. As we mentioned, our scenario involves treating the population as a single risk strata. So appropriately enough, we create a single strata room. and we were going to build one of those, and I'm going to want to store that to a variable. Now already you see we can use our editor's tooltips to help us understand what we need to provide to this function. If we hovered over the name build there with the mouse, we would start to see some of the doc string for this function. And you can see what we need to provide to this function in order to construct the single strata room. In this case, we'll need an IPM, which is our compartment model, our disease model, an which describes our movement mechanics. Init is an initializer instance. This is what's going to set up our initial conditions. Our scope is a geoscope, which describes the geography that we want to simulate over. Time frame is the simulation time frame, so a start date and end date for our simulation. And then various of these models will require parameters, and we can sort of provide a dictionary of parameter values in order to provide parameter values to our model. All right, so let's get started constructing our room. And Epymorph provides a library of built-in components to help us do this, or we could build our own if we wanted to, but we're going to keep it simple here. So if something that comes in off the Epymorph kit import is this IPM library. So we can do IPM dot, that gives us the IPM library. And we already talked about using an SIRS model. Thankfully, we've got one of those built in. And I'm going to instantiate that model and pass it in for the IPM argument of this function. Similarly, we have a library of built-in movement models under the namespace. And in this case, we are going to want to use the Centroids movement model. Okay, now we will describe our scope. And if you recall, we wanted county level granularity. So I'm going to start with a county scope. And we want all of the counties in those 4 states. So we'll do in states, Arizona, Colorado, New Mexico, and Utah. And I also need to know which year I'm going to consider the geography for. And so I'm just going to use 2020 as the geography standard here. Of course, geography can change over time. We're using census delineations here. So we want to be specific about which geography year we're using. Now we construct our simulation time frame. And we said January 1, 2020 to June 1, 2020. Okay. Next is the initializer. We also have a library of built-in initializers, but of course you can create your own. In this case, the single location initializer is going to do what I'm interested in doing here. So it's, there are lots of ways to think about setting the initial conditions for your simulation. There's not just one way to do it. But a very common way is to basically start with all of your population in the susceptible compartment of your disease model, and start with a small initial infection seed in one location, perhaps. And that's where you start your simulation. You run it forward and see how the pathogen will spread from that initial pool of infected individuals and spread not just throughout that one location, but also the other locations due to movement dynamics and so on. So in this case, for the single location initializer, I specify the index to a location. So location 0 here is just the first county in our geoscope. If I wanted to, I could be more specific about that. Just for the sake of this example, I'm choosing the 0th index, or the first county, because that's as good as any as far as I'm concerned. And for seed size, I'm going to say 10,000 individuals. So we're going to start with 10,000 individuals in the infected compartment, or infectious compartment. That's maybe a larger number than most people would use, and that's really just to sort of speed up the flow of the simulation, so we get some nice fast results to look at. Okay, and the last step in constructing our room is providing a parameters dictionary. Now, various parts of our room, the IPM, the movement model, potentially the initializer as well, are going to need parameters. But if you're not very familiar with the IPM and the movement model that you're using, say, you may not know which parameters you need. So we provided you a way to query the room to learn that information. So what I can do is print the room.params description. And if I run that, I get a description of all of the parameters that the room, as I've configured it, is going to need in order to run. So we've got things like the IPM needs a beta parameter, and that is a parameter that describes the infectivity of the pathogen. So if a susceptible individual and an infected individual come into contact, what's the general likelihood that they will that will lead to an infection event? So this parameter affects that quality of the disease model. Again, if we wanted to look into the construction of this model, we could look at the mathematical equations that govern that relationship and so on. But that's sort of a conversation for another talk. Right now, we can just sort of take these all at face value. And in this list, we also get information about the type of the parameter. So these are going to be float values and the maximally allowed shape for that data. And by shape, I'm talking about the shape of an array that we would pass in as an acceptable beta value. Now, this sort of we have a system for denoting the dimensions of arrays in terms of the simulation properties. So T stands for the number of days in our simulation, and N stands for the number of nodes in our geoscope. So when I say T by N, I mean an array. You know, if you're familiar with NumPy, you'll be familiar with working with multi-dimensional arrays. T would be the first axis, the length of the first axis, the number of simulation days, and would be the second axis, the number of geonodes. But this shape describes the maximally allowed shape. So effectively, I'm saying beta can vary over time, and it can vary over node, or both, but it doesn't have to. So I'm free to pass in, say, a scalar value for beta as well. Epymorph gives you the flexibility to do that. And that just means that if we passed in a scalar, beta remains constant over time and constant over space. So you have flexibility with certain of these parameters, and beta, gamma, and psi, which are our IPM parameters, all sort of follow that mold. Our movement model, on the other hand, has a different set of requirements. So the movement model wants to know what our population is. You know, it wants to know the centroids of all of our geonodes. That's how it's going to calculate the distances between all those nodes, and so on and so forth. So effectively, this is the list of attributes that we need to provide to our room. And you'll see some of these attributes do show up multiple times. So our initializer wants to know the population of our geography, of course, and that's in order to set up those initial conditions. And the movement model also wants to know population. We can provide the same value for both, or if we really needed to, we could provide a different value for each of those, but that's more of an advanced feature. And there is one additional way to look at this same information, which provides a little bit of a different view on it. And that is to print the requirements tree of the room. And so now I get the same set of parameters, but I get more information about what has been provided and what has not yet been provided, and so on. So you'll see values listed in red here if there is no value, listed in blue if there's a default value that's being used, and if it's in white and it lists something after the arrow here, then this means there is a value being provided to this attribute. This meta geo label attribute is something of a meta parameter that allows you to provide alternative labels for your geonodes, which can be helpful in certain circumstances. Most of the time, this will just be filled in automatically for you from the geoscope. So this is sort of a special attribute that gets special treatment. Okay, but for the rest of these, let's go ahead and start filling in values. Now I'm going to fill in values that aren't too important. I'm not going to spend very much time talking about the particular values and what they mean in this simulation. Suffice to say that these are values that produce reasonable results that model how pathogens work in the real world. Okay, so beta, gamma, psi are one thing. I'm just providing scalar values for those. Population, on the other hand, is maybe more complicated, we need, again, there's a lot of counties between these 4 states, and we need a population number for each one of those counties, right? It would be pretty tedious if I had to go look that up and maybe copy and paste a bunch of numbers in here. I could do that if I wanted to, but what Epymorph does is provides some data fetching utilities called Adrios that can go and fetch data for us based on how we've configured our room, and they're flexible in that way. They're very intelligent data fetchers. And so I'm going to use one of those here to fetch population values. I'm going to have to import those separately. So I'll go back up here, do from epymorph.adrio, import ACS5 and US Tiger, because I know I'm going to use values from both of those. And now what I can do down here is say, give me ACS5 population, and I instantiate that Adrio. And that's it. That's all I have to specify for that parameter value, and it will sort of Epymorph will go automatically and fetch the appropriate population data for us. Okay, if you're not very familiar with ACS 5, what that means is ACS 5 is a US Census data product, the American Community Survey 5-year data. And so it's a US Census data product that's published every year. And one of the things that it includes is population data. It includes a lot of demographic data and so on and so forth. There's lots of values in there. One of them is population. Now, ACS5 may not be perhaps the best source of population estimates. There are other sources out there, but this is one, and it's convenient and it works for our purposes. Notice I don't have to tell this Adrio what year of data to go get or which locations to go get. It figures all of that out by basically looking at the room configuration. So when this Adrio is evaluated, it knows the scope and the time frame in which it's being evaluated, and it can figure all that out for you. So long story short, that's going to be enough for us to pull population data. And similarly, I can do this for the centroid. US Tiger is a set of geography data files, also published by the US Census. And so this is an excellent data source for pulling geographic information. One of the things that we can get out of that is an internal point, which we can use as a centroid for each of our counties in our scope. And then finally, I'm going to also provide a value for commuter proportion. And you may recall that this is being filled in from a default, or was being filled in from a default, so I don't have to provide a commuter proportion value if I don't want to. But in this case, I'm going to overwrite it, again, just for the sake of getting a more rapid response in our simulation output. If we increase the amount of movement that's happening by tweaking this parameter, then we would expect to see our disease spread more rapidly, naturally. Okay, so with those parameters filled in, I can run this again. And now you can see that all of these values that were red are now white. And it does also tell you the name from your parameters list that is fulfilling that requirement. So we'll not worry about GPMs right now, but our IPM needs a beta value, and that's being filled in by the name star star beta, which is what this name is expanded to behind the scenes. But effectively what this tells us is that our room is fully specified and it is ready to run. Okay, so how do we run a simulation now that we've got our room all set up? This is fairly straightforward. We just create a basic simulator and we pass our room as the argument to that. Basic simulator is the simulator that is designed to run a single realization of a forward simulation. So this is exactly what we want. I can call sim.run to run the simulation once, and we'll see that produces an output. So I want to store that to a variable. And another nice thing that we have in Epymorph, but is entirely optional, is I can run this simulation within a sim messaging context, and what that's going to give me is a nice progress bar in my Jupyter Notebook while I run this. Okay, so let's go ahead and run it. And what we see is right away our AGRIOs go out and fetch the data that we need. You can see it takes a couple of seconds to do that. Then the simulation starts. It tells us our date range. There's 152 days. It tells us our little bit of information about our geography. So we've got 141 counties between these four states. And then we got a progress bar there, which is now 100, and it took about just under 13 seconds to run. And that's all it takes to run a simulation. And that brings us to part 2 of this talk. Now, it's helpful to think about what we expect to find in the output. So if we think of Epymorph as a spatiotemporal model, right, or a simulation with both spatial and temporal components, then we would expect our output to also be spatial and temporal in nature. If you think back to our compartmental model, pretty much the main thing we are worried about is what are the number of individuals that are in each of those compartments at every point in time and for every discrete location in our simulation or geonode. So every county that we're simulating, how many people are susceptible, how many are infectious, and how many are recovered sort of at every point in time. So that really defines the dimensionality of our output. But I first want to put a little bit more complexity on the question of how Epymorph handles the time axis. So the default unit of time in Epymorph is the day. You'll see that our simulation ran for 152 days. We defined a time frame from one date to another date, right? Basically, the smallest number of time steps that we will see in an Epymorph simulation is, in this case, 152 days, or the number of days in our simulation. But because we're using tau leaping as the underlying computation mechanism here for computing or for running our forward simulation, we can actually run our simulation at time steps that are smaller than one day. And at the moment, that is controlled by our movement model. The way that we inject movement into the computation is we perform movement, then we evolve our disease model, and then we perform movement again and perform our disease model, and so on in sort of this turn-based fashion. Well, the movement model allows us to break that day up into smaller parts for the benefit of our movement simulation. And we can find this information as well by looking at the room tau step lengths. And that's going to tell us our tau steps, or the lengths of the fractional days that we are going to break each simulation day up into. So in this case, 1/3 and 2/3. 1/3 is the first step of the day. 2/3 is the second tau step of the day. And so ultimately, because there are 2 tau steps in this simulation, we will see 152 times 2 total simulation time steps, which is 304, right? And the movement model has chosen these particular fractions, 1/3 and 2/3, to, again, mimic human commuting patterns. So it's very common to model people going to work, and they're there for maybe 8 hours of the day, and then they come home and spend the rest of the day, where they start. And so as we start to look at our output object, we will see that time dimension is represented as 304 simulation time steps. And that also corresponds to 152 total days. Okay, with that complexity out of the way, we can ask ourselves, what are the values of those compartments over our simulation? And first, we'll look at, well, what is this compartments? You'll see it's a NumPy array. And because it's a NumPy array, we can ask for its shape. And so we see that this particular NumPy array is a 3-dimensional array. And our first dimension is the number of simulation steps. There's that 304. Our second dimension is n, or the number of nodes in our geoscope. There's 141 counties. And 3 is the number of compartments in our disease model. This is an SIRS model, SIR being the 3 compartments. So we've got 3 compartments. So this array, if we just print out that array, is going to show us for every simulation time step, for every geonode, and for every compartment, how many individuals were in that particular cell of that 3D matrix um, for the whole simulation. Above and beyond tracking the compartment membership or the compartment population over time, we also keep track of the transition events. So every time an individual transitions from susceptible to infected, we also record that value. And this is also a NumPy array. So we can ask for its shape. And you'll see that this is also 304 by 141 by 3. That's simulation time steps, nodes, and events. Now there happens to be also 3 events in this model. If we think back to that SIRS diagram, in fact, we can re-render that diagram. So here is our SIRS model. We've got 3 compartments, which are the boxes here, but we've also got 3 arrows, which are the transition events. So this S to I transition, this I to R transition, and this R back to S transition, which represents sort of a waning immunity following recovery from infection. So again, that's why we see 3 events and 3 compartments. Not every compartment model has that same structure, of course, but this one does. We can also ask our output object for the initial conditions. And here we get a node by compartment array. So every row here is a county, and then this is S, I, and R for this particular model. And you can see here's our 10,000 initial individuals. This array was calculated by the initializer that we specified. But if we want to know what the actual starting conditions were, we can query that out of the output object. So this is excellent if you need to do your own calculations, if you really need to access the underlying data from the simulation. It is, of course, all there for you to do with what you will. And if you're familiar working with NumPy arrays, this will be a very natural way to work with that data. But we also have a number of built-in visualization tools that very quickly will help you visualize your output, understand the results of your simulation, and do some fairly involved data processing. So one common thing you'll want to do with an output is to look at it as a line plot. So we have some built-in tools for that. Out.plot.line is a function that will allow us to very quickly generate a line plot. And this is a fairly complicated function signature, but effectively what I need to do is provide a geo axis, a time axis, and a quantity axis selection, and it's going to plot the line that corresponds to that selection. What I mean by a selection here is, if we think about geography, time, and compartment quantity, so like compartments or events, right, as being the 3 axes of our output objects or our output arrays here, then we may want to subset our geography or look at all of our geography or potentially group and aggregate some of the geography together. So, these strategies that we provide for each of these 3 axes will let us do these tasks. So we can start by creating a geo-selection. We start from the scope of our room, out.room.scope, and we say select all. So for our starters, I just want to simply graph everything. So I'm going to select all of my geography. For time, I start from the room's time frame, and again say select all. And for quantity, we start from the room IPM, and let's maybe select the compartments because it's handy to just focus on either compartments or events. And if we plot that, we get a lot of lines on here. And this chart, as it is kind of a lot to look at. You can't really gain a lot of insight looking at this. And that's because, remember, we've got 141 counties and we're rendering all of those. And that's 141 times 3 compartments because we're looking at all of those compartments. There's so many lines here that we don't even try to draw a legend on this plot because it would be pointless. There's too much to look at. As well, we get sort of this odd sawtooth ribbon effect on the lines. And that is purely because of the way that our movement model works and how we've split the day up into multiple task steps, remember? As people move around, they're not in their original location. And so you sort of get these inter-day fluctuations in the populations if you don't otherwise account for that. Now, we are going to account for that by taking all of the values that belong to the same day and aggregating them together. And again, this selection utility will let us do that. So if we want to select, again, starting from all of our time frame in our simulation, we can now group by day and aggregate. And what that means is we get rid of that inter-day variation by taking the 2 tau steps in every day and simply summing them together. So this is easier to read, but again, there's so many lines in here that it's hard to make any sense of it all. So let's maybe reduce the dimensionality of our geography a little bit by grouping by state and summing those together. So instead of looking at every county individually, I just want to look at the 4 states and what their compartments are doing. Okay, so we're making some progress here. Now we have enough or a few enough lines on this chart that we can actually draw a legend. And we see we get Arizona SIR, Colorado SIR, and so on for all 4 of our states. And this is getting a little bit easier to visualize, but still a lot of lines to, I'm a little bit colorblind myself, so I can't really distinguish what all these lines mean. But if we focus down a little bit more and maybe rather than plotting SIR for all of the locations, what if we just focus on I? What's the infectious compartment doing over time in each of these 4 states? And now we've got something that we actually can interpret and draw some interesting insights from. So now we just have 4 lines: Arizona, Colorado, New Mexico, and Utah. And remember, we are summing together the compartments for all of the counties in those states over time. And we can see, Arizona starts out as a non-zero value because that's, again, where we started our infection. The single location that we seeded an infection into was in Arizona. And so our infection starts there. Eventually, it starts to pick up, and it hits a peak maybe a little bit after New Mexico does, but it certainly hits a much more extreme peak, and it rises a lot faster than New Mexico does. And that's because the infection started in Arizona. The counties in Arizona are going to be most strongly influenced by the other counties in Arizona because they tend to be closer, right? And then New Mexico follows along second because those counties are also pretty close to Arizona counties. And then we see that the infection pretty soon after that starts to take off in both Colorado and Utah, and those peak at roughly the same time. So, we could say that Arizona and New Mexico are strongly linked, and Arizona and Colorado are maybe slightly less strongly linked, but they are linked in about the same magnitude as Arizona is to Utah. And so this gives you a sense of the power of our axis strategies, how we can select, subset, group, and aggregate in order to produce charts that are more useful and more interesting. And we can do this very quickly. Line plots is not the only built-in visualization tool. If I change this for, let's do out.map.choropleth. Now, if I run this as is, we are going to get an error because, and it tells us we need to make sure that our time aggregation reduces the time series to a single scalar point. And that really makes sense if you think about what we're doing. So a choropleth map is a geographic map where all of the polygons are colored according to some data value, right? And it's naturally very difficult to show time series information on something that's a static image like that. So effectively, we need to take our time series data and collapse it down to a single point. If we take our entire time series, and if we don't group it, but we just aggregate to using the maximum value across our time series. So we are going to take our entire time series for each of the lines, pick out the maximum value, and just report that one value for the time series. So we're collapsing the time series down to its maximum recorded value across time. Now, if we run that, we can actually generate a map. And so we get this nice little plot here, Arizona, Utah, Colorado, and New Mexico. But, maybe I want to ungroup these counties, because now we can potentially visualize and make sense of all of the counties individually. And if we rerun that, it does take a little bit of time to fetch the underlying geography for the first time. Now we can see some interesting patterns on the maximum infection over time. And Maricopa gets hit very strongly. It's a very large county. And here we'll see other populous counties over time. So this is just a brief example. It can get pretty complicated in terms of what you want to visualize on a choropleth map. And we have options on the choropleth map to, for instance, transform the data and show a slightly different quantity, and so on and so forth. But again, this is just to give you a taste of what we can do very quickly with Epymorph. Another way of analyzing data is to use tables. So we have various kinds of tables that we can compute for you. If we want to see the quantiles in the time series, that's out.table.quantiles. If we want to see the a time series quantile information, then we can ask for that. Let's get the 0%, 25%, 0.5, 0.75, and 1.0 quantiles. And we'll do that, let's say, for every county, for the whole time series, and maybe now we can look at all of the compartments as well. And if we do that, we get, for every county and for each quantity, we get the quantiles over time. So the sort of minimum number, or let's focus on I here, the minimum number of infected people in Apache County, Arizona, in this simulation was 746. The maximum was 10,564, and the median for the day, the median day of infectiousness was 1,267.5. So we can compute a table of quantiles here. And once again, all of these selectors work exactly as we expect them to. So if we wanted to look at that information on a state-wise basis, we could do that. So now we get Arizona, Colorado, New Mexico, Utah, and so on and so forth. Again, I could collapse this down to a specific compartment, or I could even look at some of the events. So if I wanted to look at the S to I event, which is new infections, I could focus in on that event. And the sort of the worst infection day in Colorado throughout the whole simulation was 54,000 new infections. All right, so these built-in tools, they do allow you some customization. They do have some options to allow you to do things of that sort. But these tools may not give you everything you need out of the box. We've tried to hit, maybe the top 80% of use cases that people will have. Again, to provide a quick way to analyze this data and break it down, draw some interesting insights, understand what your simulation did, and you can verify that it was correct or not correct. And maybe looking at some of these visualizations, you would say, oh, clearly this parameter wasn't quite right. I need to tweak that parameter, so on. But if your needs for sort of crunching these numbers is more complicated or more involved or more specific than the tools that we've provided, we didn't want to entirely leave you out in the cold because we really think that these axis selection, grouping, and aggregation strategies are really useful tools for breaking down this data. if you had to do those calculations yourself, that would be potentially a lot of work. So we wanted to provide you a way to use that same functionality, uh, but outside of the context of one of our built-in tools, and that gives you a lot of flexibility. So we have this munge function available, and if I import that, I need to pass in my output as the first argument, and then I provide geo, time, and quantity selections. And now if I run this, what this returns is a data frame, in this case, pandas data frame, and it is the result of applying our selection strategies to our output data, but in a very generic and reusable form. So we get, here's our time steps here from 0 to 303. It's 304 time steps, recall. The county IDs here, and because I've selected the S to I event, I get S to I events here. Or sorry, these are state IDs, of course, because I've grouped by state here. If I once again take that back to all, now I get county information. But this allows you to use our access strategies to munge the data. And again, you just get back a data frame, which you can do with what you want at that point. It's really up to you. All right, now that we're familiar with a particular output from a simulation and the tools that we can use to very quickly visualize our results, let's look at how we can leverage Epymorph's modular design to very quickly experiment with variants of our simulation. So I've cheated here a little bit and pre-copied in the exact same room configuration that we had above. SIRS model, centroids, counties in those 4 states, etc. And if I were to run that requirements tree again, you'd see that's still a complete room. But let's say, for instance, that instead of needing an SIRS model, maybe I'm interested in also modeling hospitalization. So if we discover that our hypothetical pathogen might cause hospitalization, and we might be worried about the hospital capacity burden due to this pathogen, we would want our model to also represent the total number of people who are hospitalized over time so that we can make inferences about that. So what I'm going to do here is change our SIRS model to an SIRH model, which is very similar to the SIRS model, but includes a hospitalization compartment. And what we'll see is that just by changing this one line, I can very rapidly test a different hypothesis about the course of this pathogen. Now, running this requirements tree again, I can see that we do actually need 2 additional parameters here, and that's just to illustrate that by changing the model, sometimes you will change, of course, the required parameters. It's using the same beta, gamma, psi parameters, but then adding hospitalization probability, which is what's the likelihood that if you become infected that you will then need to go to the hospital, and hospitalization duration, how long you would be in the hospital as a result. So we just need to add 2 more parameter values here. Say a 10% chance of being hospitalized. And maybe you'll be there for 8 days on average. Running this again, we now see that once again our room is fully specified, fully parameterized. Okay, now what we need to do is run that again. You see a very similar process kicks off. It's using the same Adrios as it was, same number of days, same geonodes, and it's just going to process through that for about 13 seconds again. All right. Now that we, again, have an output object, we can do some plotting of that to figure out what went on. So let's do another line plot. And I'm going to group by state again, sum those all up. Look at our whole time series here. And we'll do the group by day and aggregate trick again to get rid of the interday variations. And let's say I'm interested in looking at the S to I event and the I to H event. That's new infections and new hospitalizations. And if I render that, we get this plot. So we can see for each of our 4 states, the number of new infections per day and the number of new hospitalizations per day. It's still a little bit difficult for me to tell apart the different lines in this chart. So, uh, for instance, one of the little customization options that we provide is to pass kwargs or keyword arguments uh, to each of the lines that are being drawn by this function in a very similar way as you would if you were drawing this yourself with Matplotlib. So one of the things that Matplotlib allows us to do is apply line styles to the different lines. And I'm going to say the first line that we draw is going to be a solid line. The second line that we draw is going to be a dashed line. And then for the third line, we're going to go back and do solid again. For the fourth line, it's going to be dashed and so on. And that's basically the same order that we see in the legend here. So effectively what this is going to do is draw all of our S to I lines as solid lines and all of our I to H lines as dashed lines. So that gives us a way to distinguish a little bit better between these two lines. I could apply more kwarg styles. I could colorize maybe all of the Arizona lines the same and so on and so forth. But this is just to very quickly illustrate that you do have some customization options available to you. Now again, this is for the state level, but of course we can always refocus back down on the county level if we're interested in making sort of county level inferences or doing a county level analysis. For instance, rather than selecting all of our counties and then grouping by state, I could select by county and then name a set of counties, let's say Maricopa, Arizona, and Coconino, Arizona. And if we focus in on those two counties, then we can see the differences here. This is a little bit difficult for the scale, of course, because Maricopa is such a large county that it kind of swamps out Coconino. But nevertheless, we can focus in to different parts of our output that we're interested in looking at. And so that's one example of how we changed, again, just this IPM, and we provided a couple of new parameters, and we were able to make a very different kind of simulation very quickly. And you could imagine swapping for a number of different IPMs and seeing what kinds of outputs you get, swapping different movement models and seeing if that tells you something more about the reality of your simulation. Or we could potentially, model the same pathogen in different locations or different time periods and so on and so forth. We can do that all very quickly. Just to demonstrate kind of the extreme end of the examples that we can simulate in Epymorph, we did one here pre-computed for you at the block group scope. So in the census tract or census geography delineations, it goes state, then county under that, and then each county is made up of a set of census tracts. Each census tract is made up of a set of block groups. And so we can go down to some very fine scale simulations here just by creating a different scope. Here I'm using an SIRS IPM again, and this pay movement model is a different kind of movement model that, rather than basing movement purely on distance, this one bases its movement on provided commuters data. So here we are loading commuters data from a data source called loads, which again is a US Census product that tells you in a very granular sense how many people live in one place and commute to another place for work. Now, as I mentioned, there's a lot of block groups here, so we pre-computed this so you don't have to watch the progress bar go by. You can see the simulation involved 4,773 distinct locations, with they're all census blocks, or census block groups rather. Same number of days, and this one took 2,300 seconds. I'm not sure how many minutes that is, but I think it's about 40 minutes. But there we go. And just to illustrate that we can run the simulation, and then by, again, using our built-in plotting tools, here we are just grouping by state. So we've taken all of the census block groups in Arizona, added them all up, and this is what our infection curve looks like. So that's just a very basic demonstration of the power of Epymorph's modularity to very rapidly produce variations of a simulation. And we think that that will allow you to test out a bunch of different hypotheses um, very quickly. And with that, I will thank you for your time. Hope that this has been helpful and illustrative to you. And I'll just remind you one last time that you can download Epimorph from PyPI, get more information from our documentation site, and please do feel free to get in touch, give us feedback, report bugs. Um, any and all feedback is welcome while we are in this beta period, certainly. And thank you again.